You click a button and the entire interface freezes. Scrolling stops working, hover states fail, the application has hit a dead stop. This is rarely the result of a classic infinite while loop. It is often a failure to manage asynchronous scheduling, specifically a recursively chained promise resolving in the background. The event loop is the architectural requirement that determines if your application remains responsive during high-volume traffic. This system map lays out the complete runtime architecture. We have the JavaScript engine with its call stack, the host environment providing web APIs, multiple distinct task queues, and the event loop router orchestrating them all. Designing a performant application requires predicting the exact order in which these specific queues process data. JavaScript is strictly single-threaded. There are no native asynchronous features built into the core language specification itself.
Inside the engine, operations run on the last-in, first-out call stack. The engine processes only the topmost frame. To bypass this bottleneck, JavaScript relies on its host environment, like a browser, to provide external APIs for background operations. When a script runs, standard synchronous commands execute immediately on the stack, but an asynchronous command, like setTimeout, is immediately handed off to the web APIs. The engine itself simply moves on to the next line of code. JavaScript executes synchronously. The host environment provides the concurrency. Once the host environment finishes an asynchronous task, like completing a countdown timer, it needs a way to send the result back. It uses the Microtask Queue. A setTimeout callback passes from the web API into this first-in, first-out holding area. The event loop continuously monitors the call stack. Only when the stack is completely empty will the loop pull exactly one callback from the Microtask queue onto the stack. This dictates why setting a setTimeout with a 0-millisecond delay does not execute the code instantly. The callback is sent to the web API, then to the Microtask queue, and must wait its turn until the primary execution stack clears. By moving exactly one macrotask to the stack per cycle, the environment prevents the single-threaded engine from being overwhelmed by simultaneous events. However, not all asynchronous operations share the same priority. The Microtask queue is a specialized high-priority lane reserved specifically for immediate state resolutions, like promise.then and .catch reactions, or mutation observer callbacks. Introducing the Microtask queue bypass lane. When the call stack empties, the engine must execute the entire Microtask queue completely. New microtasks are appended and processed immediately. The Microtask queue is completely blocked until the Microtask queue is empty. If a microtask recursively schedules another microtask, the queue never empties. This creates a condition known as microtask starvation. The environment becomes trapped processing promises and cannot cycle back to handle user input tasks like mouse clicks or scrolling. This is why the recursive promise chain caused the UI freeze in our opening example. This map adds the browser render pipeline, which calculates styles, layout, and painting strictly between macrotasks. To perfectly sync with the monitor's refresh rate, request animation frame bypasses macrotasks entirely, executing callbacks in a dedicated phase immediately before layout and paint. Combining DOM updates with layout measurements incorrectly causes a severe performance bottleneck, known as layout thrashing. This occurs when a script modifies a CSS style and then immediately requests a dimension like off-width in a tight loop. Normally, browsers batch DOM mutations and process them asynchronously. But requesting immediate layout measurements abandons the batching process entirely. It halts JavaScript execution to perform a synchronous reflow, forcing the engine to recalculate page coordinates for an accurate pixel value. To maintain 60 frames per second, developers must batch DOM read operations before their write operations, ensuring the rendering engine operates on its natural cycle. Efficient client-side code is achieved by mapping your instructions directly to the runtime's internal traffic rules and priority lanes. The universal priority order dictates every operation. Execute the call stack to completion. Completely drain all microtasks. Execute the render pipeline. Then pull exactly one macrotask. Repeat. This side-by-side comparison displays the browser's HTML living standard next to the Node.js libuv architecture. Node lacks a render pipeline, but features distinct execution phases. It also introduces process.nextTick, a queue that drains before promises, giving it the highest priority among asynchronous operations. When applications require heavy, compute-bound processing, like image manipulation, the single thread is no longer sufficient.
Here, web workers serve as a specialized solution, providing background concurrency through isolated memory and asynchronous message passing. Internalizing these priority rules shifts the focus from simply writing code that executes to predicting exactly how a system responds under a heavy volume of competing tasks.